So, gravitational potential will probably be a familiar concept for you from GCSE. However, at A-level we need to start to look at a few different things here. Okay, so you may already have the idea that gravitational potential is the energy required to move something with mass. Okay, and it's the idea that if I was to pick something up, like this textbook for example, then I am doing work against gravity to raise its position relative to the Earth. That's a new workout routine. Hope you like it. So, when you move mass, you do work against gravity. Now, you'll be familiar with the idea of potential difference when it comes to electricity, and you'll be familiar with the idea of using V for that because you associate it with voltage. Now, what we're looking at is gravitational potential, okay? And this is also a potential difference, so again, we're going to use the letter V. So gravitational potential, or more specifically the change in gravitational potential, is the work done, or the change in work done, per unit mass. So by definition, gravitational potential is work done per unit mass, but there's a little bit extra that I need to add on. Okay, so gravitational potential has got units, joules per kilogram. Okay, now what you need to get your head around here is the idea that in order to get to a point where the gravitational potential is zero, okay, then you have to do work against gravity. So, in reality, gravitational potential is a negative value, okay, when you're starting at the Earth. So at the Earth's surface, gravitational potential has a value of 100 megajoules per kilogram. And in order to get to, I'll get rid of that, don't get negative zero. In order to get to zero, you need to do work against gravity. So, let's have a look at the equation. Rearranged, if we wanted to calculate the amount of energy to raise a mass through the gravitational potential, then it's work done, it's gravitational potential times by mass. Okay, at the surface it's 100 megajoules per kilogram, and this rocket has a mass of 1,000 kilograms. Multiply these two together, we get 1 times 10 to the 11, which is also known as 100 gigajoules, or 0.1 terajoules. Now, this reference point here, this value where gravitational potential could possibly equal zero, is infinity by definition, and that's something that we'll look at with another equation in a future video. Okay, so for 2 marks here, it's not enough just to refer to this when we're defining gravitational potential. In order to raise something to a point where it's at infinity, work needs to be done, and vice versa if you're doing the work against gravitational potential. So, definition here, gravitational potential is work done per unit mass, as discussed, required to move a small mass from infinity to the point that you're moving it to. Okay, you must refer from moving it from infinity to the point to your 2nd mark for that definition. Okay, we know that gravity is not constant all the way around the Earth relative to the surface, so we discuss it as 9.81. However, if you go at altitude or you start to move away from Earth, that value will change. There are points of equipotentials, and you can think of these as contour lines on an Ordnance Survey map. So there will be a ring around the Earth where it is 100 megajoules per kilogram. You change your separation from the Earth and that value will change. We refer to this as a potential gradient when we're moving away from the Earth due to this change in potential. Potential gradient is this value of gravitational potential divided by the change in separation, which I'm using the letter R, and you'll be familiar with the concept of radius. You must refer to it as change in separation, however. Please note that gravitational field strength is what we refer to with stuff moving towards the Earth. When you're moving away from the Earth, that is a negative because that's potential gradient. Gravitational field strength is the equivalent of the negative of potential gradient.